Can folks in the chat hear me okay? Wonderful, thanks. Okay, so as always, don't forget the seating survey. The exam is hopefully going to be ready to be released at 5 p.m. today, due on Sunday. I've given you this extra day for it so that anybody that is wanting to make sure that they can get it done with before bleeding into the holiday time frame, you'll have an opportunity to do that. There is a logistical thing associated with the exam I want to make sure we go over very quickly. So you remember that I have tried in the previous exams to make sure that that none of the answers that needed to be entered required scientific notation. As you've probably discovered, trying to do pH problems and concentration problems with very low solubility products, for example, it's hard to avoid scientific notation in these. So I have found a way within Blackboard to be able to do that. I sent around a Piazza message about this, and it's going to be part of the instructions on the exam. But I want to talk you through how we are going to do scientific notation in these questions. And when it is necessary to put something in scientific notation, the question will specifically say that. And so this is what you need to do when you're at those particular questions. We're going to use what is known as Excel form scientific notation. And that doesn't mean we're using Excel, it's just they use that in this type of scientific notation in Excel. So if you have an answer that is something like 1.234 times 10 to the negative sixth, then this would be entered as 1.234 E minus 6. Okay, so the E here is read as times 10 to the. Okay, so what I will also be doing in the questions is I will be specifying the number of significant digits to report in these. So if I say for this that report it in scientific notation with 3 significant digits, you need to do it as 1.23 E minus 6. Because the way this works is that there's a pattern match for this as a string of characters that I'm going to be using. And I am going to be giving some leeway in like the last digit. So I'm going to say it has to be 1.2, but then this one could be any of like 2, 3, or 4, something in that neighborhood, e to the minus 6. And so any of those would work. But if you add another digit after that, it doesn't follow the pattern that it's looking for. So the idea is that you have to enter the answer in this format in order for it to be able to recognize the answer correctly. So, so some questions on the chat. To clarify, there's no space between the E and the numbers. That is correct, no space. Why can't we just do multiple choice for the scientific notation problems? Well, the problem with that is that it would be very, very difficult for me to come up with all of the possible wrong answers that people could come up with when they do the calculation. And so it's a better test of your understanding if you do the calculation and you put your number in. Will all numerical answers be in scientific notation? No, they will not. So when you have something like a pH or a POH, for example, where it's a normal number, then you just enter that number, and it's going to follow the same rules that we've used previously for those. I'm planning to only ask you to use the scientific notation in cases where scientific notation is really necessary. If you'd have like 5 or 6 zeros on one side or the other if you didn't use scientific notation or something more than that. I'm going to set it up, I hope, so that that you could enter a positive one. So if the answer was something like 1.6 E 12. So if it's a big number, I'm going to try to set it up so that you can either do it E12 or E plus 12. If it needs to have a negative sign in the front, you can put a negative sign there. I'm going to also try to have it set up so that the E can be either the lowercase or the uppercase. But there are only a limited number of things that I can do to in this. I can't. It would be difficult to put in all of the permutations of doing things slightly different, like putting in spaces or something like that. So at some point, I have to draw the line between figuring out how do I code it to do it that way versus how do I actually get through all of the questions on the exam. All right, any other questions on this aspect here? The instructions that talk through this are going to be on an actual, are going to be on the exam itself, so you can refer back to them if you need to. Do we need a plus for positive answers? No, you do not. I'm going to try to set it up so that it won't count it wrong if you use a plus for positive answers, but you do not need to use a plus. Anything else on this? Okay. I am about 2/3 of the way through writing the exam, so I will. I know some of what's going to be on it. The rest of it, I am still trying to figure out. And I'm going to be very busy this afternoon, making sure it's all working right. And I don't think any of the things that are going to be on the exam are going to be surprising. We have in the last few class periods worked quite a bit on solubility products and using tables of solubility products to figure out what's going to precipitate, what's not going to precipitate, how much will precipitate, those sorts of things. We have spent some time on titrations as well and doing calculations in titrations. And within titrations and the related concept of buffers, we really get at most of the concepts within acid-base behavior. So those are going to be the two major sections. There will probably be a handful of unrelated questions to those two main sections. So something on relative strengths of acids, looking at things like the oxidation number of a central atom in an oxo acid, for example. Or maybe one question. I don't think I would do more than one question on Lewis acid-base behavior. So most of it's going to be in those two main kinds of categories, a titration/buffer kind of system and a sort of a complex, by complex I mean multi-component, not as in it's really hard, but a complex precipitation system. So where you'll have more than one or two things that are part of it. Any questions on that kind of stuff, on what to expect on the exam? No? Okay. So there really weren't any Piazza questions for muddiest points. So what are people feeling the least confident in that I can try to go over again, or maybe from a different angle, to try to help make sure you're as ready for this as possible? Can we do more examples of the titration/solubility stuff for the exam? Certainly. So what kind, let's do titration first. What kind of titration problem would you guys like me to talk through? The two examples that we have looked through in some detail were the one that's on the exam, right? So the two examples that we've gone through before is a strong acid, strong base titration, which is extremely straightforward, and a weak acid, strong base example. There's a request on the chat for a weak acid, strong base example. I'm happy to do that. Okay. And clarification on when to use moles versus concentration in ice tables. Okay, we can talk about that as we go through the example. That's a good question. All right, we've done acetic acid almost every time, so let me find a different weak acid to look at. Let's do, what do I want to do here? How about, that's a pretty small one. Okay, let's do hypochlorous acid. So hypochlorous acid, which has the chemical formula HClO. Okay, and this has a pKa of hypochlorous. Why is it listing two different pKa's? That's weird. Okay, we'll take the 7 point. No, let's do a different one that has actually has only a single one listed. We'll do citric acid. Citric acid is, now that's a polyprotic. Do we want to do I don't think we want to do a polyprotic. That's, I'm not going to have you do a titration with the polyprotic acid. I'm sorry, I should have prepared one already. We will do lactic acid. So lactic acid is a component of milk. We have CH3H5, 5O3, and it has a pKa of 3.86. All right, so we're going to do a titration of this. Let us, in the previous examples we've done, we have chosen the same concentrations for the acid that we're using and for the base that we're titrating with. So let's add the extra complication now of those being slightly different. Okay, so let's suppose that we have a 0.100 molar solution of lactic acid. So let's call that HL. We'll do L for the lactic acid. And we'll say we have 25 milliliters of that in our beaker that we're using. And we are going to titrate this with, we'll use a strong base, sodium hydroxide. And let's say that we are using 0.200 molar sodium hydroxide that we are titrating it with. So the general idea would be to try to identify, you would be told what volumes of added sodium hydroxide to calculate the pH at. So the first one is almost certainly going to be before adding any NaOH at all. So in that case, we have only the acid reaction going on. And so we should write down what that acid reaction is. HL aqueous plus H2O liquid is in equilibrium with L minus aqueous and H3O plus aqueous. My pen is running out of ink. Let's try switching to green. Okay, so in this scenario, we know our initial concentration of lactic acid because we haven't diluted it at all yet, 0.100, 0 and 0. Minus x, 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 0.100 minus x, x, x. So I did that very quickly. Does anybody need any clarifications on how to do that quickly? Okay. So our Ka is equal to 10 to the negative pKa. So we have the 3.86 there. And this is going to equal our concentration of products over our concentration of the acid at equilibrium. We have x squared on the right-hand side, and let's make the assumption that x is small compared to 0.1. We'll see if that's correct in a moment. So, calculator. Come on. There we go. So we want the pKa of 3.86, change sign, 10 to that power. This is 0.000138. We multiply that by 0.1, and we take the square root. So we find that x equals 0.0037, off the bottom, 372. That is our hydronium ion concentration. And we see that this is indeed small compared to this. So this is about a little more than 3%, a little less than 4% of this, and our cutoff typically is around 5% for whether this is an okay thing to do. And so our pH is going to be the negative log base 10 of this number, and so our pH is going to be 2.43. Okay. So, so in the case before we have added any sodium hydroxide, all we do is the weak acid reaction as written. Any questions about that? Okay. So let's now move on to a case where we have added some sodium hydroxide. So let's say we add 5 milliliters of sodium hydroxide. So what we do at this point is that we need to start tracking moles of the acids and the base that we're dealing with rather than the concentrations, because the volumes are changing as we add more stuff. So from here on out, we need to deal with moles and then convert to concentration before we do the ice tables or before we do Hinders and Hasselbalch. So this is where we're aiming, but let's do some prep work here. So if we have initially 25 milliliters of our lactic acid, and if our concentration is 0.100 moles of lactic acid per 1 liter of lactic acid, and we convert 1 liter to 1,000 milliliters, liters, we are left with how many moles of lactic acid we started with. So 25 times 0.1 divided by 1,000 is 0.0025 moles of lactic acid. In our 5 milliliters of sodium hydroxide, let's see how much sodium hydroxide we've added. So 5 milliliters NaOH. Our concentration here, remember, we decided to do a different concentration this time, 0.200 moles NaOH in 1 liter. 1 liter is 1,000 milliliters. And so we get 5 times 0.2 divided by 1,000, 0.001 moles of sodium hydroxide added. Now, the way we handle this is to look at what the sodium hydroxide is going to do to the lactic acid we started with. So if we have lactic acid, HL, and we add hydroxide to it, then the hydroxide is going to pull off the hydrogen, the acidic hydrogen from the lactic acid. We get L minus plus H2O. So what that means is that after the addition of the sodium hydroxide, our concentration of HL is going to be 0.0025 minus 0.001, because this is how much of it has reacted away. So it's going to, I'm sorry, this is not concentration, this is number of moles of lactic acid, is going to be 0.0015 moles HL. And our number of moles of the lactate ion, which is the the conjugate base of lactic acid, is going to be that 0.001 moles. Okay. Does that step make some sense to people? Or excuse me, let me ask it the other way around. Are there, yes, there, so somebody wants me to explain that again. So the idea is that we have added hydroxide to the system, but there's no hydroxide in the reaction we're just looking at up here. So we need to think about what the hydroxide is actually going to do. The hydroxide is a strong base. And so when coupled with a weak acid, that strong base is going to pull the proton off of the lactic acid. What that does then is it uses up all of our hydroxide, and then having used up all of that hydroxide, we can go back and use the same equation we had before. That's the goal of what we're trying to do. So we view the hydroxide as something that converts HL into L minus. How much does it do it? Just by how much sodium hydroxide we had. So this amount of sodium hydroxide becomes the amount of the lactate that's formed, and we subtract it away from the amount of HL that we started with. Well, those are the number of moles. What we want, though, is concentrations. So our concentration of HL is going to be those number of moles over the volume that we have. So we started with 25 milliliters of the HL, and we've added 5 milliliters of the sodium hydroxide, so we have 30 milliliters now. You can either write that as 30 milliliters and then do a conversion from milliliters to liters, or you can directly write 30 milliliters as liters, which is what I did right there. And we find that our HL concentration at this point is 0.0015 divided by 0.03, or 0.05. Did I do that right? That doesn't sound right. 0.0015 divided by 0.03. Nope, that's right. So 0.05 molar. And our concentration of L minus is 0.001 moles over that same volume. So 0.001 divided by 0.03 is 0.0333 molar. Now that we have these concentrations, we compare them. And so can anybody remind me what the criteria are for when we can use the simpler Henderson-Hasselbalch equation versus when we should use an ice table? Chat says between a 10-90 and a 90-10 ratio. Yes, that's right. So if one of them is within 10% of the other one, basically, or of the sum of them, then that's generally considered that it's okay to use the Henderson-Hasselbalch equation. Well, a 3-to-5 ratio is easily within that range, so the Henderson-Hasselbalch equation works very well in this case. So we write down that Henderson-Hasselbalch equation. pH equals pKa plus the log base 10 of the concentration of the conjugate base over the concentration of the acid. Our pKa was 3.86, log base 10 of 0.0333 molar over 0.05 molar. So I still have that value in. I divide by 0.05. I take the log base 10 of that, and I add it to 3.86. And we find that our pH equals 3.68. Okay. So, so somebody says, can I explain the 10-90 and 90-10 ratio again? So the idea is that in the case where the ratio of these concentrations is between 1/9 and 9/1, when it's in that range, this equation is an acceptable way to calculate the pH. The reason for that is that this equation assumes that when we do an ice table and we do a shifted initial conditions on the ice table, it assumes that the X's are going to be small compared to this concentration and this concentration. Okay. If we are outside of this range of the 1-9 and the 9-1 range, then the math works out in a way where those tend to not be able to be ignored. And so we do need to use the ice table and then write it out in its full quadratic equation glory. Yes?
So in the group project, we had to shift our answers when using the Henderson-Hasselbalch equation. How come we don't have to do that here?
So the procedure that we followed right here was doing that initial shift. That whole idea of adjusting this, the HL and the L- concentrations so that we're getting rid of the hydroxide was doing exactly that. Okay, that was a good question. All right, so this is what we do now when we are in the buffer region. We use the Henderson-Hasselbalch equation, and we tell we're in the buffer region by doing this analysis to see how close are these two to each other. Let's now, so we've done 2 points. We've done no added sodium hydroxide and 5 mils of added sodium hydroxide. Let's do one where, let's see, I'm thinking about my concentrations here. That's twice as concentrated, 25. Yeah. Let's do one where we've added 12 milliliters of sodium hydroxide. So the equivalence point is going to be 12.5 milliliters. So we are a little bit shy of the equivalence point. So let's take a look at that. We have the same result from before about how many moles of HL we started with. So we have number of moles of HL initial is 0.0025. Our number of moles of NaOH that we've added is going to be 12.0 mils 1 liter, 0.2 moles, 1 liter, 1,000 mils. Mils cancel, liters cancel, we're left with the moles. So we get, in this case, 12 times 0.2 divided by 1,000, and we get 0.0024 moles of sodium hydroxide. So when we look now at the amount we have after we shift the reaction, after we let the hydroxides react away some of the HL, we find that our HL amount is going to be 0.0001 moles. And our number of moles of the L minus is going to be 0.0024 moles. Okay. When we look at these two, they are clearly outside the 9:1 or 1:9 ratio. So we are going to end up having to use an ICE table in this case. So our concentration of HL, we still need it in concentration in order to do the ICE table. We take the number of moles divided by our volume. Our volume in this case is 12 plus 25, or 37, 0.037 liters. So 0.001 divided by 0.037 gives us 0.027 molar in HL. Our concentration of L minus, 0.0024 moles over 0.037 liters. So 0.0024 divided by 0.037 gives us 0.065 molar. I did something wrong. I think I didn't put enough zeros on that top one. No? Oh, I didn't write enough zeros on the top one. Okay. So this is there, 0.0027 molar. Okay. All right, so we have our concentrations here. We now need our ICE table. So HL, aqueous, plus water, liquid, equilibrium with L minus aqueous, H3O plus aqueous. We've already done our shifted initial conditions, which is what this whole process up here was doing. We have 0.0027, 0.0650, minus x, 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 0.0027 minus x, 0.065 plus x. And because normally when we have one of these problems, I would say try ignoring the x's and then check the answer again to see if that was a valid thing to do. But in this case, because we observed that this ratio was too big, we know that we're already in a situation where we cannot ignore those x's. So we need to write out the full equilibrium expression. So our Ka equals, we calculated that earlier, so 0.000138 equals 0.065 plus x times x over 0.0027 minus x. So we can multiply through. 0.000138 times 0.0027 minus x equals 0.065x plus x squared. Multiply those through. 138 times 0.0027 gives us, I'm going to go to scientific notation, 3.726 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8 minus 1.38 times 10 to the negative 1, 2, 3, 4 x equals the same thing on this side. So let's combine terms. So x squared, we take 0.065 plus 1.38 times 10 to the negative 4. So we have plus 0.0651x minus 3.726 times 10 to the negative 8 equals 0. And we go find ourselves a quadratic formula calculator. Or you can use the quadratic formula if you prefer to do that. So our A coefficient is 1. Our B coefficient is 0.0651. And our C coefficient is negative 3.726 times 10 to the negative 8. And we get one positive answer where x equals 5.72 times 10 to the negative 7. And so our pH is going to be the negative base 10 log of that. So 5.72 times 10 to the negative 7. And we find that our pH is going to be 6.24. Okay. Once we are at, so that gives us now a case in between the buffer region and the equivalence point. Yes?
How did you know what the equivalence point was?
How did we know that what?
What the equivalence point was?
Okay, so the equivalence point is the point at which you have the same number of moles of the acid and its and the added sodium hydroxide. Okay, so in this case, when we did the calculation, we found that we had slightly less sodium hydroxide than the acid that we started with. Okay, so at the equivalence point, it would be 12.5 milliliters added. Let's do that calculation next. And we can tell that from the volumes and the concentrations here because the sodium hydroxide is twice as concentrated as the HL. So half the volume of the sodium hydroxide will be the same amount as we had there. So that's how I knew it was 12.5. Okay. So let's do that 12.5 calculation now. We can short circuit this one quite a bit because we know how much HL we started with is 0.0025 moles. We now know we've added the same amount of the sodium hydroxide. Oh, excuse me, NaOH. So when we do this shift, what we have done now is we've reacted away all of the HL to make L minus. So our number of moles of L minus is going to be 0.0025. And our number of moles of HL initially is going to be 0. So this situation now is one where we have the conjugate base, but we aren't starting with any of the conjugate of the acid that we started with. And so because of that, we now have to deal with the conjugate base's base reaction rather than the acid reaction we were dealing with before. So our base reaction is L minus plus H2O is in equilibrium with HL plus OH minus. Zero 0.0025, 0, 0, minus x, 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 0.0025 minus x, x, x. We will see if we can ignore that to make the math easier. KB, which remember equals KW over the Ka of the conjugate acid, equals concentration of HL, concentration of OH minus over concentration of L minus. So we have our Ka from earlier. So we're going to take 10 to the negative 14 divided by 0.000138 to get a Kb of 7.25 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that is equal to x squared over 0.0025. So times 0.0025, and I'll take the square root, and we get that x equals 4.26 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. Okay. So that is our hydroxide ion concentration. So our POH equals 6.37. And so our pH equals 14 minus that, 7.63. Any questions on any of the steps up to that point? Yes?
How come we can assume that the x is small if it's larger than the 9-to-1 ratio?
Because, okay, so assuming that it is small in this case is saying that we are starting close to equilibrium. But this wasn't one of those cases where we were trying to see, can we use the Henderson-Hasselbalch equation? Okay, so when we're using the Henderson-Hasselbalch equation, there'd be a value here with the x rather than it just being an x. And that one is much more about, can we ignore it here than it is about, can we ignore it here? Make some sense? Okay. Good question, good question. Okay, so the only regime we haven't talked about yet is what if we add more than the 12.5 milliliters? What if we are in the region past the equivalence point? And so if we add, let's say 15 milliliters of sodium hydroxide. Well, the amount of HL we started with, again, is the same. The amount of sodium hydroxide we've added is going to be 15 mils, 0.200 moles per liter. 1 liter, 1,000 milliliters is 15 times 0.2 divided by 1,000 is 0.003. And so our number of moles of HL at the end is going to be 0, because we have more sodium hydroxide than HL. Our number of moles of L minus is going to be 0.0025 moles L minus, because all of the HL has been converted into L minus. And there is now some hydroxide that has not fully reacted away. So the excess hydroxide is going to be 0.0005 moles hydroxide. In this case, because we have passed the equivalence point, this is going to do nothing. That's just going to be stuck there, and you're going to get almost no HL back. So all we do at this point is just take this and say that's our hydroxide ion concentration. So our POH is going to be 10 to the negative, the base 10 log of that, 0.0005 minus 3.3. And so therefore our pH, not minus, our pH is going to be 10.7. Yes? Oh, we do need to do concentration. Yes, thank you, my bad. So this is wrong. Thank you for the correction. So concentration of OH minus is going to be 0.0005 moles over our total volume. 15 plus 25, that's 40 mils. So 0.0005 divided by 40 times 1,000. 0.0125, a bit different. POH is 1.90, and so our pH is going to be 12.1. Thank you for the correction. Question from the chat, how did you get the moles of OH minus? So we started with 0.003 moles of sodium hydroxide. 0.0025 of that was reacted away as we converted HL into A minus, and so the amount that's left over is simply the difference of these two, so 0.0005 moles. Welcome. So those are, what you see there is that there's really just a handful of ideas, even though there are these different regimes that you have to do the calculations in. The first idea is, I've got too many pages, where can I find it? The first idea is the interconversion of the acid and its conjugate base based upon the amount of added base that you have, so that you're getting your starting amounts of the acid and its conjugate base. The question at that point then is, what do you do with that information? What you do with that information then is you see if they are within the 9:1/1:9 range, you use Henderson-Hasselbalch. If they're outside of that range, but you still have some of both, then you use an ice table. If you have so much base that's been added that you have passed the equivalence point so that there's no HL left, then you just use that extra amount of base. So that's the way to think about it, is this reaction that happens, look at the concentrations you start with at that point, you're dealing with at that point. How close are they? What do I do with it? Yes?
So for the 1 to 9, 9 to 1 ratio, is that the concentration or is that the moles?
Should be the same thing because they're going to be in the same volume. So the volume would cancel out anyway. For the chat, the question was the 9 to 1, 1 to 9 ratio, is that for concentration or is it for the number of moles? And the answer is both of them because it's equivalent. The ratio is equivalent. Okay, do you feel a little better about titrations now? Yeah. Yes, what can I do for you?
So like if we have a question about this on the test, like what would the question be like? Would we want to find like the pH after a certain number of milliliters has been added?
Yes, almost certainly. So it would lead up to it somewhat. So I would make sure that you know how to do the conversion from like a pKa to a Ka. I would then tell you the concentrations you're dealing with and see and have you do some calculations at certain amounts added. So how could this get more complicated is the question to think about. There are two ways it could probably get more complicated. One is if you're dealing with a polyprotic acid. Given the length of time on an exam, I am unlikely to ask you to do that. You might, however, expect to see a titration curve for a polyprotic acid and be asked to interpret it. But I would not be having you do calculations on that kind of thing. The other possibility would be doing the titration the other way around. If you have, say, a weak base and you are adding a strong acid to it, so that instead of going from low pH to high pH as you add your volume of NaOH pH. And so you've got, equivalence point, you have half equivalence point, you have your buffer region, and so on. You could imagine me asking you to do volume of HCl that's being added to a weak base, which then would give you a titration curve that would look something like this. The concepts are all identical. There's nothing there's nothing different about what you do. All you are having to do in this kind of situation is make sure you're tracking, am I talking about OH minus or am I talking about H3O plus? And you ought to be paying attention to that question anyway. Okay, so we have about 10, 12 minutes left in the class period. So I kind of feel like this is enough on titrations and buffers at the moment. There was one person that requested, okay, well, here's a question here. There's a couple of questions. So in that example, then you would you start with the base equation and then change to the acid equation after the equivalence point? Yes, that is exactly what you would do. You start with the base equation and you're doing the conjugate acid equation after the equivalence point. So there was another question here doing a brief example of oxidation numbers of a central atom. Absolutely. So this is frequently done for what are known as oxoacids. So there's a good series of these. We looked at phosphoric acid, we looked at sulfuric acid and sulfurous acid. There are chlorine-containing acids as well. There is ClOH, there is ClO2H, ClO3H, and ClO4H. Okay. So if we look at the Lewis structures of these, the chlorine it looks like this for the first one. The second one, we have that. The third one, and for the fourth one, we have so these are called oxo acids because the hydrogens are attached to oxygens, and those oxygens are then attached to a central atom of some sort. Okay. So the thing that is going to matter in these cases is what is the oxidation number of these chlorine central atoms. Okay. So if we go through and look at oxidation number, what do we get for the oxidation number of chlorine in this case right here? Chlorine is less electronegative than oxygen. Need me to review how to do oxidation numbers? Okay. So remember that that I made the analogy to formal charges. And the idea of a formal charge is saying that when we're doing the accounting system for where electrons are, we split electrons that are in a bond equally and give them to their adjacent atoms. So in this case, what we would do is take the core charge of chlorine, which is 7 because it's in group 7, and we count up the number of electrons, 1, 2, 3, 4, 5, 6, 7, and so this would have a formal charge of 0. Oxidation number makes a different assumption. It says, give both of the electrons in the bond to the more electronegative atom. In this case, the more electronegative atom is oxygen. So in this case, we would start with the same core charge of 7, 6, 5, 4, 3, 2, 1. This has an oxidation number of +1. Okay. Let's now look at the oxidation number of this chlorine. We start with the same core charge of 7, 6, 5, 4, 3, +3. What would the oxidation number of this one be? 5, correct. What's the oxidation number of this one? 7. And so the way this affects acid strength is that the higher the oxidation number, the more the electron that are around the oxygens are being pulled towards the chlorine. So the easier it is for the hydrogen to come off, and so therefore the more acidic it is. So this one is going to be most acidic. This one is going to be least acidic. Any clarifications on any of this? No? Okay. Anything else? Why don't I throw up the topic list from Piazza. And we have a few minutes left. We could talk about things if we wanted to. Where am I going? Share screen. All right, so here we go. So topic list. So there's the acid. I need to switch this over to. Okay. So there are the acid, base, and buffer topics. And I'll scroll down in a moment for the others. Folks ready for me to scroll down? I know that some people on Piazza were getting kind of confused about converting between molar solubility and KSP and what each of those mean. Is anybody here still confused enough about that you'd like me to go over that? Seeing some, okay. I'll do that relatively quickly. So remember that, so I'm going to use as an example aluminum phosphate. So, nope, I'm not going to use that. I'm going to aluminum sulfate, SO4. It's a 2 minus, so 2 of those, 3 of those. There we go. Hope you can read through my scribbled fixes. All right, so 2Al3 plus SO4 2 minus, and there are 3 of those. So if we imagine this as an ice table, then, and we are just dissolving it, then we're going to have a 2x and a 3x here. And so our equilibrium constant, our KSP, which is going to be the concentration of Al3 plus squared times the concentration of SO4 2 minus cubed, then if we put in these values, we have 2x quantity squared 3x quantity cubed. So we end up with 4 times 27 times x to the 5th going on here. Yes. Thank you. Speak up on this. Sorry, and I did that here too. My bad. All right. So talking through it, Al2SO4 breaks into 2 aluminums and 3 sulfates. We have a 2x here, 3x here. Our KSP is the aluminum concentration squared, our sulfate concentration cubed. We have the 2x that goes in here, the 3x that goes in here, so we end up with 4 times 27 times x to the 5th that we have. So some people were confused about feeling like we're double counting things if we put the 2 both here and here, but they're coming from different places. This, the one inside that's the coefficient is coming from the stoichiometry of the ice table, whereas the exponent is coming from the structure of the equilibrium constant. Okay, so you do in fact have it in both places. So this is how to deal with KSP. But what is the molar solubility? The molar solubility is how much of this dissolves. So if we imagine this, even though it's a solid, even though this is not something we include as part of the equilibrium constant, we can still think of this as minus X. We're still losing this amount of stuff. So the molar solubility is X. That's it. Okay. So here we have a KSP where we have 5 concentrations. So in a sense, this has units of molar to the 5th. But the X is always going to be in molar because it's going to be how the concentration of the material that you dissolve when you treat it as the formula unit. Okay. There's another question here. Can we? Let me first ask: is there any more clarifications on this that people need? No? Okay. So there's a question over selecting buffer components. So the first thing is, I'm going to actually go back to our lactic acid example. Here we go. In order to have a buffer, you have to have an acid and its conjugate base. And you have to have them in close to equal amounts, somewhere in the 1 to 9 to 9 to 1 range. So if you pick one component, the other component is simply its conjugate. That's it. In terms of which one to pick for a particular application, what you want to look at is the Henderson-Hasselbalch equation. So the buffer regime is where the concentrations of the acid and its conjugate base are close to each other. If they're exactly equal to each other, then the log base 10 of 1 is 0, and the pH becomes the pKa. So usually somebody decides what buffer they want to use based upon a pH they want to be stabilized. And so whatever that pH is, you go look for an acid that has a pKa that's right close to that. So that's how you pick buffer components. Lewis acid questions. Had previously thought I'd said I wouldn't ask any Lewis acid questions. What I said was I wouldn't ask many, and I think there will probably be not more than one. The idea of a Lewis acid is just electron pair donor, electron pair acceptor. And so if you have some kind of Lewis base and you have some kind of Lewis acid, they undergo a reaction to form Ba, where the B is donating both electrons to it. Oops, sorry. Then this is simply identifying that this is a Lewis acid-based reaction because of the donation of the electrons. That's really all I would go for, and I will promise you I am not going to make that kind of question tricky, because I know that we have not emphasized it in class, and so I'm not going to be pushing for subtleties on that one. Okay. All right, well, I have run us out of time. Thank you all very much. Thank you all for having some good questions today. It always makes teaching easier when there's some good questions to work with.